Good morning. Can you hear me? Not sure where everybody is, but I sent a message. I don't like to have to send the link. I think people know it's class and they don't have to they don't have to prepare, they don't have to drive, they don't have to do anything but turn on their computer on time. And this is where we at. Where we are at. I do not think I have to send the link, but I sent it. So we left off last class with the discussion of regression. And I asked you to work through the rest of the notes on your own. And I promised you I would show you how to make a regression line in Excel. Now I have an Apple computer, so it looks a little bit different than maybe the computer that you have or that what you're looking at, but it's still Microsoft Excel. So what you have to do, so these are the data that we used last time. So you have to put the data like the table here, right? And then you have to say, let me start fresh. Let's start fresh. So let's start here. All right, so what I want to do is see if I remember the steps. Okay, so I want to go to Tools. Okay, I can do this. I can get the data analysis in statistical form. I can get all the results in a table. So here it asks me to put in the Y and the X range. I can say okay, and then it gives me this output. Somewhere in between. So it provides me this output. And you have what's called multiple R square, adjusted R square. So these are all measures that with one variable, with only one explanatory variable, they will be the same. It calculates something called standard error. So we're not used to looking at this, but we will look at this kind of a table later in the course. So these are the calculations, like the steps to calculating really attesting the significance of our result. These are the coefficients. So this for the X variable, which we only have one of them. Its coefficient is 2. In other words, it's the number in front of the symbol X is 2. This is the slope. So coefficients are slope terms. And since we only have one variable, this is the slope of X. Then we have some more calculations here. And this is called the p-value. We're going to talk more about p-values towards the end of the course as well, but just for now I'm showing you this sort of table. Okay, so you'll see this again later. Now, what you're probably more interested in is getting this. So how do I get this chart? So I have to make a chart. And the way that I do that is why am I not remembering? So it's not insert. Okay, insert. So you have the equivalent thing in Excel that you have. And what you want to pick is, if you pick recommended charts, you get all the options. So this is pretty much the one we want, right? But let's see, I want to scatter. So let's see, I have to remember what I did. If I pick this one, what happens here on the left over here, on the left under home, it says add chart elements, and you'd have the equivalent type thing. This is really where I want to go, where it says trend line. So you want to go to trend line, find out where trend line is, and you want to pick linear. So you get a linear trend line, and then you want to also get those other things. You want the equation of a line and the R, right? So here's more trend line options, and I go here, more trend line options. Can you see all this? Let me check. Oh, you don't see that. Okay, let me put that on the screen. Let me get this on the screen. Okay, so what did I do? I did, once I got the scatter, I asked for a scatter plot. That's first step. Then I went to edit. It said add chart element. So what I want to add is a trend line. So you want first scatter, then trend line, and pick linear. So that gives me this. And then I want trend line, more trend line options, and that will give me these options over here where I ask to display equation on the chart. You see I put up this equation here, and the R square value. So that's what I get. Very simple equation, right, where the intercept is actually understood to be 0, right? Because it goes, if you extend this line here, it'll pass through 0. It doesn't always have to be 0, it could be another number, but that's where it hits this axis. You can change all the options. I think I inserted, to get the one here that I made, I inserted axis, and I filled that in, and then I changed the title. Okay, any questions? So the main points are, I'm going to put them in the chat, is that you want to use scatter, and then trend line, and then trend line options to get this. So you can practice that if you like. Any questions? So I asked you last week to work through, oh, how's the sound, by the way? Can I ask you? Is the sound all right? Okay. So no questions about that? So those steps, scatter, trend line, and trend line options. So this was the mess we ended up with last class, and I asked you to work through this on your own. I asked you to make all these calculations. Very simply, once we see the graph, we can see, or the scatter plot, we can see that this has an R1, and the slope, we interpret the proportional relationship as 2, so that turns out to be the slope. I can do this, I can make these calculations in my calculator. I taught you how to do that, and I showed you how to get it in Excel. What I left you with was computing these values in Excel. So actually getting the covariance and the correlation, and ultimately finding the slope. Then I told you this is another way to see the data. So this one is called historical type data. Okay, so there's this kind of data that is based on a past time period. So this is collected from prior observation. We'll call that ex post, or after the fact, or historical data. That's different slightly from ex ante data, where this represents a probability distribution that's derived from using past data, forecasts of the future, including economic forecasts, okay, not just information about the BCE returns in relation to a broader market index set of returns. So what's important for you is that this has this extra column, which is the probability of this event happening. So this is actually a discrete distribution, even though it looks a little more complicated than the ones, oh well, what you might think of. This is a discrete distribution. Did I spell that wrong? My goodness. I spelled it wrong. Discrete distribution. Have I been spelling it wrong? Discrete distribution. Oh, you can spell it. Discrete is a discrete person, and discrete is the way I've been spelling it. Okay. I second guess myself now that I'm learning Spanish. Okay. Okay, discrete distribution, because there's 3 possible outcomes, and these are the pairs of values that occur if there's a boom economy, if there's a normal economy, 50% chance, these are the returns, and in a recession, these would be the returns. So with this kind of data, I left you to calculate the weighted mean, the weighted standard deviation, the weighted covariance, the weighted correlation. This is the most easy, this is a simpler way to view the formula for doing that, but I spelled it out, which looks way more complicated. But it shouldn't be complicated when you understand that this is analogous to the one we have above, but for ex ante data. So I left you with those results so that you could calculate this on your own. And I'm just going to double check. I don't have the values here, but I did put the tables in Excel, in Moodle. You should have the tables that guide you along. And did I put the results? No. but I think I put them in Moodle. Let me check in Moodle. Let's see Moodle. Just checking that it's all there, because I do update my page every semester, and usually everything comes over to the new page, but sometimes I need to check. Okay. All right, so let me show you what I'm looking at. I'm right here looking for Moodle. I'm just positioning the page. This is a lot of steps here. Okay. Oh, why is it showing me that? Not sure. Weird. Try that again. There you go. So this is the Moodle page, and here you go. This is the information. These are the results. This is the solution. So you could go step by step. Can you see that? And calculate the solution. Why didn't that work? So I just opened up that link, and this page opened. Where you have the results, okay? So you can see that the results are all here. The mean, standard deviation for each variable, the calculation of the covariance, and the calculation of the slope. So you should go through those, okay? You should go through those for both the ex post data and the ex ante data. Okay, so here's, if I click on that, this opens. And again, I have to position this. And you see the results are below, okay? And I start working out the mean for X, the mean for Y, etc. Any questions? So all I want to do right now is I'm hoping that you had a chance to watch my videos and you reviewed the calculations for making a line. If you haven't, you're going to have trouble understanding what I'm going to do next. So that will be for you to review. Okay, so those results, those calculations are all in Moodle under Solutions. So what I want to do is go back where we left off. So I asked you to watch this video on on the equation of a line. So if you didn't, please watch that. And then I'm going to go here. So we're going to spend some time on the derivation of the prediction line. The derivation of the prediction line is based on finding the line that floats best between the points such that the distance between each value and the line above in total is identical to the distance from each observation below the line to the line in total. Okay, so that's how we're going to rest this line. So it fits closest to all the points in the vertical direction. Right. So how do we got to give a name to this distance, so we're going to give the name residual. And the residual is calculated by the value, the height, the vertical value of the observation minus for this level or this value of x that corresponds to the first coordinate, right? Where would it fall on the line? That's its predictive value. So this is the observed value. This is the predictive value for this value of x. So I'm going to I'm off, so I'll fix that a little bit. That fits better here. Okay, so this is called the predictive value, and this is called the observed value. And I'm looking at the value of the second coordinate here. So let me add. I'll just call it x. Okay, so this is the value of x. This is the value of y, and there's two different y's. So the one for the exact point, which we call y observed, and the one for the predicted point, y predicted. And I subtract y observed by y predicted, and I get this difference. This difference here is called the residual. I can also write that as y, because that's the value that was observed, and differentiating with the hat symbol, sombrero symbol, this will be the value of y predicted. Okay, so this, let me just remind you for people who are just still confused what I'm doing. This traces back to here. So this is y. That's y observed. And this is y predicted. And the difference between the two is the residual. The residual will be a positive when the observed exceeds the predicted. So here, residuals will be positive and below the line will be negative. This says positive. So why do I care about the residuals? Because that's what I look at. I want to minimize so what I want to do is I want this to float so that it fits perfectly to offset the positive residuals and the negative residuals. Okay? Another way of saying that is I want to focus on this distance here. So let's draw some residuals. So like this and this and this. So these you imagine these floating pieces of string. If I was to join them all, their sum total should be the same as this below. In this will be the same as minimizing the total length. If I was to connect all these distances, okay, these strings, I want the minimum string, so I could refit different lines one after another, and I want to use the line, the one I pick is the one that produces the minimum string. So we want to minimize the residuals, but not precisely the residuals. We have to be careful because some residuals are positive and some are negative. So what we end up doing, just like we did with the standard deviation and calculating the variance first, we had to square the deviations from the mean. In this case, we have to square the residuals to remove the sign, the negative sign. And what we are going to do is we're going to pick the line that fits such that it minimizes the sum of the squared residuals. Okay, now you're not going to have to do this. I'm not going to have to do this, but in principle, this is what is happening. And there is a pattern to doing this from the if you use if you take a mathematical approach to this and you make a general stab at it, you find a pattern. Okay, and that's all we're going to focus on. The results of the minimization of the least squares prediction line using ordinary least squares, which is the technique I've just described, results in giving you this line. I'm going to maximize this. Now this looks like the equation of a line, except that I put a hat here. I should actually, so in mathematics we write the line is equal to y equals a plus b x, right? In mathematics, that line goes infinitely in both directions. In statistics, y is just a prediction. In fact, the a is just a prediction and the b is just a prediction. These are all predicted values. This one is called the intercept, and this one is called the slope. And it's not, it's a line, but it's not going to hit all the points, right? It's going to float in a way between the points such that it minimizes the sum of the squared residuals. Now I eliminate the hat here because when you learn simple regression they just ignore that, but it is actually A and B are predictions because, again, the line doesn't hit all of the points. Okay, so it's just a prediction of the points. So we just write it like this. It's simplified like this. And it's drawn only, this is drawn and expressed oops. It only exists among the range of values of the data. Okay, so we draw it around the data. We don't imagine it extends because you can get bizarre interpretations if you try and extend that line beyond the range of values of the data. All right, so here are, in general, the results of minimizing the sum of squared residuals, which essentially means using calculus to do this. And computer programs do this, but for simple regression, and even for more complex regression, there's a pattern to the results. And those patterns use both calculus and linear algebra to derive the results, which you won't have to do. You just need to use the results. And the results are these, so you need to remember this. First, the line must fall on the point defined by the means. The mean for the x values and the mean for the y values. Remember, we were using the means in both directions and talking about how we were comparing all the values to the mean, right? The very way that the regression, the correlation is computed depends on relationship or trend in relation to the means. So this point, because this point in the x direction, x bar, is the value that's closest to all the other points, right? That's the whole idea of the center of gravity. And in the in the vertical direction, y bar is the value that's closest to all the points. In the vertical direction, again, as the center of gravity. So this point has to fall on the line. So that gives us a point. We know if we have a point and a slope, we can draw the line. So all we need is a slope. Can we get a slope? Well, yes, you can. You can get a slope. In general, a slope, the slope of the line is computed by this formula. And I discussed it last class a bit. This formula will give you the slope every time. All right, now an analogous type of formula exists when you have more than just one explanatory variable, but for this class we're just going to work with this one, okay? And I mentioned if you need to memorize this, you remember the term risk, and where we interpret BS in finance as the sensitivity of a stock returns to market performance. So it captures a notion of risk. So anyway, it's a good mnemonic that I use to remember R SY over SX. Okay, so it's always the correlation multiplied by the ratio of the two standard deviations, with Y coming first. Or on top. So what does this show me? Let's see. Well, and we did talk about this last time. The slope and the general trend of the relationship has the same sign as the correlation, right? They have to have the same sign. So that's because the standard deviation is always positive, right? Standard deviation was always positive because it's the square root of a value. Oh, Liliana wanted to see something. Do you want me to slow down? Are you talking about seeing this? Take a screenshot, Liliana. And the video, I also have an edited video for this. That's available and linked in my notes. I mean in Moodle. Okay, so there's a point. It has to fall on the line because X bar is the value that fits closest to all the points in the horizontal direction. Y bar is the value that is closest to all the points in the vertical direction. So this has to be on the line. The slope is calculated by this measure, and I explained how to memorize it. And I was just talking about the R and the B having to have the same sign, which makes sense. The slope should have the same sign as the correlation, or correlation of the values, the general trend of the values. And then with a slope and a point, we can compute the equation of a line. What we do is we take this expression and we plug in what we have. So where there's one point, we put that in here, and we have a slope, so we put that in here. And then we can solve for A. And we derive this, so I plug in all the values to solve for A, and then I use it in my equation. So these are the steps. Just one moment, I have to check something. Let's go back to the data set where I left you that data set, and I asked you to practice calculating the regression coefficient for the data. So let's go back there. And this is the data for the arm bone and leg bone measures for insect fossils. All right, so what I want to see is their relationship now, because if there is a relationship, a strong relationship, we could say that these fossils, the insects that made them, were from the same species. Okay, so we are told to plot, where are we told? So on this page, you're told to plot humerus versus femur. So that makes the arm versus the leg. Right, so it's always Y is the first one and then X. So that means that and for insects, the arm bones will be bigger than the leg bone, right? So that's X and that's Y. So I put things horizontally, but you shouldn't be confused. So what we're going to do is enter this data into our calculator to get all the information we need, okay? That's the fastest way I know. I just took a screenshot for myself. I'm going to enter this now into my computer. my phone, sorry, my app for the calculator. And this is the calculator I asked you to get. So let's enter this in with the pairs. So for the first pair would be 3841. So I have to activate second data. Here's the data. Oh, and there's something in there, right? I need to clear it. Second, clear work. So once I'm in, I can clear. And I start to enter 38, enter, and now I enter the other part of the pair, 41, enter. So now the second data point is 56, enter down, and 63, enter down. So I'll let you get organized before I continue. Get your calculator out or do this in Excel. Let me continue then. 3, it would be 59, enter, down, with 70, enter, down. And the fourth one, 64, enter, down, and 72, enter, down, and 74, enter, down, and 84. So I have them all in. And now let's review my data. So 38, 41, 56, 63, 59, 70, 64, 72, 74, 84. So everything's in there. What do I do next? Second stat. Now my linear regression output. My results, there's 5 observations. Here's the mean for X, the standard deviation for X. Here's if I considered that a population result. This is the parameter for the standard deviation. I don't want that. But here's the sample mean, the sample standard deviation, and I don't use this sigma. And here are the coefficients. Here's the y-intercept. Here is the slope term. And here's the R. So these are the results that I will use to make, well, this actually gives me the regression line, right? But if I was to calculate it, let's check the calculation. Let's see. Okay, so these were my A and B. Let's see here. So what I have with what we were doing here, the two means would be the point. And if you go back, remember the means were, or check the point, the means were 58.2 and 66. Let me go see that. Let's see. The mean for X was 58.2 and the mean for Y was 66, right? Now, I need the SY and SX. So if you go back and you take just 2 decimal places, SY was 15.89 and SX was 13.19, and I can calculate the slope. Now this is, because of the rounding, this ends up being different than the one on my calculator. Okay, but we'll go with this. Well, let's do this another way so we can do this by ourselves. Let's not use any decimal places and calculate this together, okay? So we can get practice rather than just looking at this. So let's take what we need, remember, are the mean and the standard deviations. So let's say we just had that. No decimals. Let's do this with no decimals. So this one was 58 and this one was 66. And let's go back and see again. SX would be 13 and SY would be 16. So let's calculate B. B would be R SY over SX. Oh, and R was given to us as 1 if we round it. Let's go back and check. R was given, no, it's 0.99, isn't it? Well, anyway, to round to no decimal places, it would be 1. Okay, so to no decimal places, if I rounded it, this would give me 1. If I had to calculate R, we're going to do that exercise. We're going to calculate R together as well. So it depends on the type of question you have. Here, you can use all of this, I'll say, to show me how you get B and the line. BA and the line. So now this was 1, SY is 16, and SX is 13. So 16 divided by 13 would be 1. If I don't use any decimal places, let's keep 2 decimal places for the result, or it's going to look really boring. Okay, and then we have the slope, and then all we need is A. So to find A, we take our mathematical equation of the line and we fill in y bar and x bar. And we also fill in B. So we can fill all those in and find A. So A would be y bar is 66, A plus 1.23, x bar is 58. Let me double check. X bar 58, yeah. And so A is negative 5.34. So it looks somewhat different. Still a negative. So the result that I get if I round my statistics to no decimals and then just keep 2, slightly different. So I get I'm going to use a hat because this doesn't fit all the points. It's just a prediction line. It's negative 5.34 if I did that right. You guys can let me know. And the slope is 1.23. So obviously the rounding is going to affect things. So follow instructions on rounding. If there's no instructions, keep 2 more decimal places than the original values. That's why I have so many decimal places here. Because the original values I used 2 decimal places, so I kept 2 more. And that makes sure that I have, and it's just a rule to keep my answers, make it possible for you to get the same answers as me. So rounding statistics to whole numbers. It's slightly different. Sensitive, isn't it? So what do we see? We see a slope of about 1.2. And R equals 1. What it means is that it's a very reliable relationship of 1.2 between the arms are, so let me step back a second. What's the slope again? Slope is equal to change in y over change in x. In our case, it was the y was the arm bone, and the x was the leg bone. So it says that for every extra unit of the leg bone, the arm bone is 1.2. So it's longer, right? %20 longer. Okay, any questions? Okay, no questions? So we can use this then to answer some questions about the relationship between the measure of arm and leg bone, and that's what I do in the notes. I go through several types of questions that you should get comfortable with in this unit. The interpretation of the slope is it explains the marginal effect, the effect of an additional unit of x on y. So you have to fill in the variable names to move away from this general definition. For each additional millimeter of femur, the humerus is 1.2 millimeters longer or larger. Now, that's what I just discussed. And this is a highly predictable relationship within the range of values. The range of values, if we go back and look at the range of values are between, for X, 38 and 74, and for Y, 41 and 84. But what if we go far below or far above? Is this relationship, does it even exist? Is it meaningful? What if we go all the way to 0? And that's what the intercept does. The y-intercept says, what is the value of y, the arm bone, when x, the leg bone, is 0? If you use the line as though it's a mathematical line and you plug it in, let's use the one they have here to follow with the questions. If we put 0 here, that means that y hat will be 4.1135 negative. Now think about what that means. I have a slightly different number here. I must have calculated with different. Yeah, it should be 2 ones. Just a typo. So again, this means the interpretation is when the leg bone is 0, the arm bone is -4. Now, does that make sense? Can a bone have a negative measure? No, right? It's meaningless. And that happened because I'm using the line to interpret outside the range of realism or realistic values. So it doesn't make sense. This is an example of extrapolation of the data, and it is a use of the prediction line in a situation found far outside the range of observed values. That's why it leads to erroneous conclusions. The prediction line only applies to values within or near to the range of observed values. Okay, questions? All right, no questions? So Gerardo asked, when you say near the range of observed values, does that mean that it can be outside? It can be outside, but not so far. And far, remembering standard deviation is a measure of the spread of values, so you don't be outside one standard deviation or so, okay? That will be too far. I'm giving that as a rough number. I never said that in the past, but just to give you an idea, you don't want to be in terms of the values, because near or far depends on how the values are spread out. Using the standard deviation as a kind of measure of how far away you are, don't be more than like a standard deviation outside of the range of values. And if you are, then you can be suspicious of what you've got, okay? It's not solid. You're not necessarily as convincing about your prediction when you're so far outside. Okay, so where was I? Okay, so here we are. we want to make a prediction when the femur is 60. So there's a relationship among the values. It's pretty tight. I can't remember, like the values are pretty tight, something like that. I don't have the exact graph, but you should plot it and see. And what I want to do, so there's a line that we've predicted. And what I want to do is for this value here, let's say, I'm gonna remove the axis for a moment. I'm just gonna, well, let's say the axis, let's do this. Let's say there's a break in this axis, so it's not exactly near the, don't use this as the origin or anything. Just let this be a line that's not so close. So don't use this to interpret the distance. Okay, what I'm going to do is just talk about this line in the plane, and I'm going to use it just to remind you, or let's use yellow. For x equals 60, if you go back to the data, x doesn't equal 60, does it? So we're going to make a prediction. So it doesn't equal 60. X, the best we have is 59. When x equals 59, it turns out that y is 70, right? That's what we saw back here. When x was 59, sorry, y is 70. And we'll call this y observed because we actually see it. And what we want to figure out is the residual. We want to figure out this. So the observed value is 70, and the predicted value we need to calculate. The predicted value is here on the line. So let's get the predicted value, which I also write as y hat. And how do we get that? We need to plug in something to the formula, right? The formula or the equation of the line gives us the value. So I'm going to use the form in the notes just so we get the same answer. So this was the slope in the notes. I'm going to put 60, and then this is the intercept, and I calculate 68. So this turns out to be 68.1685. So y observed is 70. And y predicted is 68.1685. Oh wait, what did I do? That's 60. I want to do 59, sorry. Wrong number. I probably should make this bigger. Do that again. Let's do that again. I'm pulling the numbers from the wrong questions. Let's do that again. So, I want this for x equals 59. So when I plug it in, you get the value. You guys should have the notes in front of you to avoid confusion. So if I plug it in here to 59, I get 66,963. So when I use 38, so when I use the line, I'm getting values on the line. So 70 minus 66.9638 gives me my residual. The residual is a positive. Okay, so hopefully that didn't confuse you. This is a different question here. This was to find a prediction when it's 60. So it was finding the value here, which would be higher, right? 68, yeah, 68.1685 would be here. So this is for the answer about finding the residual. And this is for the answer if you were to predict a point on the line. And we did both in this one. I got the prediction and I got the residual. Any questions? So I'll just go through these questions and then we'll go on to the next unit. So these are the type of questions you should be able to answer. So the residual, once again, just making the point. This distance is the residual, the distance between the observed value and the predicted. And that's what you calculated. How do you determine if an observation is an influential point? And I give you the advice, well, since an influential point is a point that has influence, that is, including it alters the measured prediction line and the strength of that prediction line in terms of like the regression coefficient being close to 1 or close to -1. If it affects those dramatically, then it's an influential point. But if you drop it from your data set and your R improves, it means it was an influential point. So it's not a good idea just to drop it ambiguously. You need to have a logical reason to drop values out of your analysis. Okay. I do have some exercises like that, and you guys should read those in the notes. Okay, so there's a measure called r squared. You saw it in the output. R squared is basically r squared. Okay, so it gets rid of the sign, and it has a new interpretation, and also has a new name. It's called the coefficient of determination. And we actually interpret this not as an index as r was. Now we interpret it as the proportion or fraction of the variation in the response variable that is explained by the explanatory variable. So in our example with the fossil data, it was 100%. The r squared was 1. So r was 1, so r squared would be 100%. So the 100% of the variation in the length of the arm bone is explained by the femur. That leaves no room for other predictive variables. So it's fully explained by X. So I just go through the types of questions that I can ask you, and they're listed here. You should be able to answer all those types of questions. And I put a line here because the 10th question, are the coefficients valid and reliable? In other words, is the prediction line valid and reliable? And this is based on the ordinary least squares assumptions. Now I'm not going to get into this. It's much more than we need to do for this class, much more theoretical. But it's really important as a consequence of this to know that there's assumptions inherent in what you're doing. This is actually the relationship in terms of Greek letters. When you see Greek letters, remember I told you we treat it like it's the population result. So this is actually an equation, like a model. This is a model that will get you all your values. So the data doesn't necessarily fit on the line. You can have a line, but then there's this extra jump term that makes it scatter. Okay, this is what creates the residuals. But in terms of the parameters, we call this the error. So this is the actual model that we are estimating. In standard regression model, we assume that the true nature of the relationship between x and y can be expressed by the population model like this, where E represents the error term since the points of observations are not necessarily on the line. Essentially the coefficients of the parameters of a linear population model. Okay, so that's what we're trying to emulate. And there's some other properties here, or assumptions that are made. That the sampling is random. That the variation of the explanatory variables is not all the same. That there's no relationship between the explanatory variables and the error. This is a really big one. If there's a relationship between them, what is it saying? It means that the explanatory variable or variables that you're using are correlated with something that you're not using. And this can bias your results. So I'm not going to say too much about this because it involves a lot of concepts that we don't have time to get into. But just to let you know, getting a regression model set of results has assumptions inherent in it, and you can read about them here. And if you've ever done regression analysis before, the important thing is to realize there's there are some tests that you need to verify to make sure that the assumptions are satisfied. And one basic one is to plot your residuals and to look to see that there's no pattern in the residuals. If there's a pattern in the residuals, it means that you missed an important variable and it's being captured in your error term or your residual term. So the residuals should really, if you plot them against x, they shouldn't have a pattern. They should just bounce around randomly around 0 line. So it's like no correlation. There should be no correlation between the residuals and the explanatory variable. There should be no pattern. They should be randomly jumping around. There shouldn't be okay, that's what it's saying. It shouldn't be like they shouldn't be, this is not really looking very good, is it? They shouldn't be getting wider as x increases. So let me write this down. Residual plots. So if you calculate a residual for every single value of x, or this is 0, this is 0. There shouldn't be any kind of pattern, and there shouldn't be a widening. Okay, these would be examples of violating assumptions. This one would be that there's a correlation between your error and some other variable, and the variable x, which means that x is correlated with some variable that you missed that should be in your model, and this shows that your variance terms aren't unequal. So you probably don't know most of you don't know exactly what I'm talking about, but some of you do, so I'm just mentioning it here. You guys can read through this. But what I want you to take away from here is that there is a model with assumptions inherent in what we're doing. That's the most important thing. This model, if you actually had the true intercept, the true slope, and the actual error terms from the line, then you would have the population model. But we don't. So we estimate alpha, we estimate beta, so this would be our A, this is our B, and this is the y hat. And we don't talk about the error term. But all of these assumptions would have to be tested. And one way to test is to do these residual plots as described. So you might see a mention of that when you're working through problems that I've given you. So you can come back and read about it here. And then I have some more discussion about that. So that goes beyond the scope of the course, but I'm putting it here for people who are familiar with this topic and want a thorough treatment of the topic. So as I said last class, just read this. It's not going to be examined. So yes, well, let me just say this. Are coefficients valid and reliable? That will depend on the assumptions being satisfied. If the assumptions are not satisfied, then the coefficients are not valid and reliable. And so the prediction line would not be valid and reliable. So most of the time I've talked about just one variable as an explanatory variable predicting the response y, but in fact in regression we use more than one variable. And the development of the model like this with more than one variable comes from the type of analysis that I've been suggesting, looking at residuals, looking for patterns, and saying, well, if there's a pattern between the residuals and the explanatory variable, there's some variable that's missing from my model that should be included in the model. And it begins a process of trying to find that variable. And I explain that process here. All right, so that's all I want to say. Again, don't worry too much if this is blowing your mind, but it's important to understand there are assumptions in our models that invalidate the model if they're not satisfied. So here are some exercises that I gave you on page 20, 21 that you should read through. They're very easy. 23 that emphasizes, describes, or illustrates the points I've been making. And then this discussion here of the calculations that you need to practice. And this is the last thing we're going to do before we go to the next unit. I want you to solve this. I'm going to give you 10 minutes to work on this. No, 5 minutes. 5 minutes to work on this problem. And then we'll review it together. All right, I'm back. I wanted you to work on this because it's not just about calculating the values with your calculator. I want you to demonstrate a few things that you understand about the calculation of R. So first, I want to get the results from the calculator as just as a goal, to give us, we know the right answer, so then we know what we're doing is correct. So let's put these in the calculator. So I'm going to go back to my data mode and clear work. So it's wiped out. And I start to enter 2, enter down, 17, enter down, 4, enter down, 7, enter down, 4, enter down, 7, enter down. And I hope I've done it all correctly. And I ask for, I can review. No, I won't just hope, I'll check. All right, so then I get the results. I can stat, and I scroll through 7 results, the mean and standard deviation of X, mean, standard deviation of Y. Remember, this is the population standard deviation. I don't use that. And then A, B, and R. So those are my results. Negative correlation of 6.67. It's not strong. So you see when the values are going up for X, Y is going down. And when the values for X are low, the values for Y are high. So there is a negative type of relationship, but it's not that strong. In this case, X is low and Y is low. And this one, X is low and Y is high. So this creates the ambiguity and makes it less close, closer to 0 than with a strong relationship. All right, so I've asked here for you to complete the table and to hand calculate R. We know R. Let's put our results down. Let me go back to that. A was 13.7. B was negative 1.7. Oh, we'll take 2 decimal places. How about that? So A was 13.67. B was negative 1.67. And R is negative 0.67. So I'll just write those here. So we have the answers, but let's do this manually. Because you might see some questions with the manual calculations. You need to be able to answer those as well. So missing values. When x is 2, what is the standardized term? So it's 2 minus 4 divided by 2. So this is -1. And what about this value here? When y is 17, standardizing 17, 17 minus 7 divided by 5. And I'm using the information here. All right, and now compute the R. I'll leave you with that for a minute. Go ahead and compute R. So this is like a show all your work exercise. If I did everything right, any comments? Okay, so then what I have to do to get R is now multiply these and you notice this is very easy because you got a bunch of zeros here. Those are all 0. This one will be -2. This one will be -2, this one will be 0 and 0. So then I have to sum, and that's -4. So what I have so far is R equals to the sum, right, of these two standardized terms being multiplied. And then I have to average, divide by n-1. So I have -4 divided by n-1. There's 7 observations. So this is 6. So R is -0.67. So that's the long way. So I did that because there was no other opportunity. I left you guys to practice with the tables on your own. You do need to know how to complete the calculation, whether the table's like this or with the deviations of the mean terms. So that's R, and then to get B, well, we're not asked for that. In part A, so let's look at the questions now. In part A, you're just asked to calculate R, so we get R equals -0.67. And then, because this was actually a quiz I gave, in case some students got the first part wrong, they had a chance in the second part where I say, okay, well, ignore what you did in part A. What if R is 0.3? Find the line. Okay, so although this is the correct answer, and the line in this answer would be y hat equals 13.67 plus or minus 1.67x, I said, forget about what you did and just let R be 3. What would be your line? I hope that's not too confusing, but it was to get students to calculate R for 1 point and then the line for another point. So if that's the case and R turned out to be 0.3, what do we do next? Well, we calculate. First, we get the point, which is x bar, y bar. So this is our point on the line, and then we get the slope by the formula sy, r times sy over sx. Which turns out to be 0.3, sy is 5, and sx is 2. And this gives you 0.75. So with a b of 0.75, then you can solve for a. A is equal, well, let's see. I'm going to do this the longer way because I feel more comfortable. So a is so we write y equals a plus bx. We enter what we have. So we have that y bar equals a plus b, which is 0.75 times x bar. So we put the slope in and the point, and I'm just doing it in separate steps. You don't have to. 7 equals a plus 0.754. So a equals what? What did you get? Are you guys listening? What is A? Okay, A is 4. Very good. So this took some algebra. It takes your understanding of correlation and a line. So there's a lot of elements here. It's a very simple problem, but it puts everything in one, making you calculate these missing values so you know how to get them, and then calculating the R, then ignoring it and getting the line. Okay, so this is our A. This is our B. And this is, well, we don't really need it, but this was the R that they gave us, 0.3. So the final answer is y hat equals 4 plus 0.75x. And that's it. And then you can use it to make predictions. You can use it to calculate residuals at certain points. And that's what I'm going to ask you for. I'm not going to ask you to test for validity of the relationship, except that I'll tell you to comment on R. And R, like not validity in terms of the assumptions being violated, but I want to know that you know how to include the idea of R. Now R here is very small, isn't it? R is equal to 0.3. It looks like a positive relationship, and it's not a very good relationship, is it? If you square R, you get 0.09. What does that mean? How do we interpret that? Gerardo had a question about why are we using 4,7? We're using 4,7 because the least square regression line must fall through this point. That was the first point I made in the summary on the last page. That every regression line falls through this point because these values are the point, the position closest to all the other points in the horizontal and the vertical directions. So, of course, the line that means to fit closest to all the points must fall there. That's how I know it's a point. And then the slope that I get is from the formula that I give you on the results of the last page, and that's how I solve this. So my question is, how do we interpret R square? We interpret it as 9% of the variation in Y is explained by X. It's very, very low, isn't it? 9%. So it's not a good predictor. All right. Okay, so I want to now, for the next half hour, introduce the next topic, unless you have questions about regression. The regression exercises, you can find exercises for review in the old midterms, obviously in the practice assignments and things I have on Moodle. But check out the old midterms because there are questions on regression in there that you should practice. Of course, as well as the homework exercises. Now with the practice assignments, it's your prerogative to try and reproduce the results. You don't just have to read them. You know, you can try and make calculations and use Excel, and let me know if you have any questions. So I want to go to the next unit. It's a big one. It's a big unit. So we're taking a little bit of a break from from the normal distribution and from the things that we've been doing so far, and we're going to get into the theory. We're going to start building the bridge. I'm going to teach you probability theory, or we're going to strengthen the bridge. And we're going to use probability theory to do that. And what you'll see in units 5 and 6 is we're going to take the bridge, and I'll make reference to this later, but we'll build the bridge and we're going to take the bridge and we're going to go both ways on the bridge. All right? So this is the idea of where we're headed. Please read these notes before next class, and I will talk about them, but where I want to really start today is an overview of probability. These diagrams, these are Venn diagrams. You may have seen these sorts of diagrams in your lifetime. I'm going to appeal to your common sense and intuition in this overview and show you and demonstrate where your thinking is logical and where you need a little refinement. I'm also going to formalize some concepts. I'm going to use some terminology so that we can speak about this in a common language. So here you have S, the space. S, it stands for the sample space. Oh, so this is in Unit 4 on page 7. So in a phenomenon that we're interested in, the possible outcomes are either A or B. That's it. When this is the case, we refer to these events as being complementary. Complementary. It's a term that's used specifically because knowing one tells you indirectly about the other, because they fill the entire space. Disjoint events appear like this. Now, in relation to complementary events, complementary events are also disjoint. They don't overlap in the same space. However, complementary events have a special additional feature that I just explained, but to reiterate, they fill all the space. Now, in disjoint events, there's A, there's B, and there's something else. What should we call that something else? Does anybody have a suggestion? How can we refer to this something else? Okay, so let's see. I can call A, and I can call B, but I can also call B I can refer to B in terms of A. Similarly, I can call A here and B B, and I can refer to this something else as not A or B. That's the event outside. It's an event. And now what I see are there's three possibilities here that don't exist here. So complementary events are just two. There's A and there's B, or in other words, not A. Or you could say there's B and not B. Okay, so they can be referred to each other, through each other. My pen is too thick. Okay, so let's backtrack a bit. Let's focus on this one. Let me add onto these events because we want to use it for probability. We're going to refer to this symbol as the probability of the event A happening. And we'll refer to this symbol. I'm going to change them. One moment. Do that again. I'm going to refer to this as the chance of A happening. The chance of A happening is 30%, or 0.3. Okay? You can think of it as 0.3 or 0.4. The chance of B happening is 0.4. Is that possible in this space here? Is this a possible description of the space here? Right, so the answer is no, because it's not 100%, so that doesn't work here. In this case, let me see how I'm gonna present all this. So with each scenario, I'm going to ask you 3 questions. What is the probability of A or B happening, what is the probability of A and B happening, and what is the probability of not A or B happening? So what's the chance that either A or B happens in this space? What's the chance of A and B happening at the same time? And what's the chance of something else happening? So let's look at the first one. Now the first one, some people will remember that this is written as probability A or B from taking this in other classes or seeing the symbols. A union, U for union, B, I'll put that there. So what's the chance of either A or B happening? Is it a possibility? Is it a 10% chance, a 50% chance of A or B happening? So if I just put myself here, what's the chance of A or B? A or B. It means to be an either A or B. The chance in this space is 100%. Or I'll just write it as 1. So that means that the implications of that are that the total of these two, their probabilities must sum to 1. Okay, it's 100% chance of seeing A or B occur. They fill the entire space and are 100% possible. When you guys are writing 50-50, what you're thinking, when you're thinking about that, you're thinking of A alone or B alone, but I'm asking about A or B. That's a different concept. Because of that first point, the probability of not A is equal to 1 minus the probability of B. They are complementary, like you saw when we were dealing with the normal distribution. Complementary events. I wrote it wrong. I'm going to say not A is 1 minus. Let me do that again. The probability of A is equal to 1 minus B. That's what I meant to say. The probability of not A, what would be the probability of not A? Just some practicing with the terminology. And to avoid confusion, I'll take this off for now. So if I said, what's the chance, this is the chance of A is happening, what's the chance of A not happening? Well, the only other thing that can happen is B. So the probability of not A is the same as the probability of B happening. The probability of not B is the probability of A happening, which is essentially what I wrote here. So just getting you comfortable with the terms. So either A happens or B happens. There's nothing else that can happen. If A happens, it means B did not happen. If B happens, it means A did not happen. And I can use that to compute probabilities. Knowing one, I can know the other. All right, think about that for a bit. So what's the chance of A and B happening at the same time? This can also be written as the intersection of events. What's the chance of A and B happening at the same time? When events are complementary, we depict them like this to reflect that A and B will never happen at the same time. So the chance of happening at the same time is 0. Finally, the chance that something else happens, by definition of complementary events, nothing else can happen. So the chance of that is also 0. So these are the same 3 questions I'm going to ask you for the next set of drawings. It doesn't matter in this case what A or B are, I mean in terms of their probability, what their probability are, because this will always be the answers. Complementary events fill the space. They are mutually exclusive. They never intersect, and there's nothing else possible. In the sample space of all possible outcomes. What about these now, these disjoint events? Disjoint events are not complementary because we have that something else, third space, or third event. It's dependent on the other two not happening, but it exists. So disjoint events are not complementary, but complementary events are disjoint. I mean, they don't overlap. So let's see. Without knowing the values, could we figure these out? A or B, again, is the event here or here, but nothing else. What would be the probability of that? When events are disjoint, if I know the two separate probabilities, I only need to add them to find out the probability of both of them, of either of them happening. So or, another way to say or is either. A way to say not or is neither. So either A or B. To actually calculate a value, it would have to give you those values. What about A and B? Do I know the chance of A and B happening at the same time? What would it be? Is it possible that A and B happen at the same time? No, because they don't overlap. So what's the chance? What would this probability be? This will always be 0 for disjoint events. Do I know what the probability of not A or B is? Could I figure this out here? How could I figure that out? Well, if I know A or B's probability and I know they all have to add to 1, all I have to do is take 1 minus probability of A or B. Okay, so intersection doesn't happen in this disjoint set of events. If I know A and B, I can calculate the chance of them, either of them occurring, and I can also compute the chance of neither of them occurring. So let me give you some values for A and B. So I'm going to use the same ones I wrote above. And you can calculate now the probabilities. So we get 0.7 for the chance of either of them happening. And the opposite of that is 0.3, but let me write it all down. You don't have to every time, but just to practice, you should. Okay. So yeah, I could expand it, but I'll just take the one from there, because I already calculated it. All right, we have a few minutes, 10 minutes, and I'll lay out the next two, and then we'll go. So these are the possible ways of seeing events. You need to know their relationship, interrelationship. and the assumptions inherent in what we're saying, okay? So complementary events are disjoint in that they never intersect. Disjoint events are not complementary though, because I'm not able to calculate one from the other. Directly. All right, what about overlapping events? Here we are. So let's do the same thing. And I will use these same numbers. Below as well. All right. Now we have the situation of overlapping events. There is a common space here where A and B do happen, so it does exist. So A or B has to be calculated differently than it was here, because if I'm just going to add the chance of B to the chance of A, I'm accounting for this shared space twice. That's not right. So when events are overlapping, or you have information that these events occur or coincide, so let's start using some examples, right? So you can follow what I'm saying, not just looking at circles in a square or in a rectangle. I use the exercise of a salon. I'm going to go to a salon actually after this class. So going to a salon, you can have your hair colored, or you could have a manicure, or you could have both in this sample space. You could also have something else done that's out here. Okay? So if we use the same analogy for the one up here, in this salon, you either can have your hair colored or a manicure, not both, but you can have other things done, but exclusive of these. So you can't have your hair colored and something else. You can't have your manicure and something else. It doesn't exist in that world. And here, a hair color or a manicure and nothing else. That's all they do. It's going to be a one or the other. Okay, so these are the different kinds of possibilities or scenarios given the relationship of the events. So in this one, I have hair color, manicure, both, and other things. Possible other services. So let's stick with saying they're overlapping. A is 0.3, B is 0.4. So what's the chance of A or B? When they're overlapping, as I explained, if you take A and you add it to B's probability, you're over counting the shared space by 1. So why don't we just take it off? And that's the rule for calculating this or that when the events overlap. So it's very important to know their interrelationship. Do I know how to calculate A and B? That's my next question. I cannot calculate A or B unless I know A and B. So because I can't calculate A or B, I cannot calculate not A or B. So everything hinges on calculation of A and B. Now, my question to you is, do I know this? And I'm only going to get my hair colored, by the way, but there are all the possibilities at my salon. So, do you know A and B, anyone? From the information given, the fact that the relationship of A and B is such that they are overlapping, do I know what the chance of A and B are of happening is? No comment? Okay. Well, I do not. I do not know what this is. With this information given, I have no way of knowing what's the chance of A and B happening. I would need additional information to calculate this. If someone told me that A and B are independent events, and I have this, so this looks a little bit different, but it's independent events are overlapping. So what is independent? How is independent different from disjoint? Well, obviously, independent is not disjoint. Independent events are overlapping events. I'm not going to write it here because that might be confusing. What I'm going to just say is independent events have to be overlapping. Okay, so independent is not the same as disjoint. It's a different concept. What it means is, and the implications are, the implication is when events are independent, it means that knowing that one occurred, so if you're, for instance, here, right? Oops. So let's say you're here. So let's say I knew I was here and here, so I know A occurred. Does the chance that B occurs in this space change? If it doesn't change, if the chance of B in the regular S space is the same as the chance of B in the domain of A, then these are independent events. For instance, we use the classic example of sequential flipping a coin. If I flip a coin, each time I flip, the chance of a head is the same. It's 50%. So let's say I flipped a coin and I got a head. So now I'm in the domain of I saw a head happen, but now let's flip it again. What's the chance of a head? Does it change just because I just got a head in a flip of a coin? No, it's still 50%. Nothing changes. That's a classic example of sequential events. In the phenomenon of flipping a coin. Let me describe it in terms of the salon. Let's say a person got their hair colored, so they're here. What's the chance that a person who got their hair colored also had a manicure? Now you could think, well, depends on the price, right? So let's say that in this specific salon, the chance of having your hair colored doesn't influence the chance of getting a manicure. So it's a high-end salon where money isn't an object. So the probability of getting a manicure doesn't change. That would describe independent events. So what I want you to do for next week is finish this, answer these questions, and we're going to start here next class, where what I'll do here is, because you need a value to finish this, I'm going to give you one. So you can solve that one, and then here I'm going to reiterate the same values. So hopefully by the end of next class you'll have a good understanding of this topic. We'll find out. Any questions for me? I see a lot of people have already gone. Hopefully everybody will take the chance, or take time to watch these videos I've produced, because I will assume that you did. Okay, so finish these off, and we'll talk next week. So have a good week. Keep in touch. I think I answered all the questions about the last test. If there's any other questions that you have about the last test, write me an email, or if I didn't get to answer your question, write me an email again, okay? But for now, I'm going to let you go. Have a good week. If you have questions, write them now, or email me, or phone me, or text me. You know, I haven't been able to find my phone, so if anyone texted me, I don't know where my phone is, so I apologize. I have to find it before I leave. What I'm thinking to do is maybe not next week, but the week after, we'll meet in a different platform, and I'll also stream it on YouTube so that you guys can talk and ask me questions. Hopefully that'll help people who prefer conversation than to me just lecturing. Well, I think we're conversing in the chat, but I think there's some people who just like to express themselves in words. Okay, bye for now.